we have got an executable that is smart enough to find security problems on its own, or at least we hope so. The next tools I'm going to show you only present tools that check for buffer or for stack-based buffer overflows. There are dynamic approaches for format string exploit and heap corruption as well. I think if you know, I think he talks the day after tomorrow, will at least tell you a little bit about dynamic approaches for heap corruption. So go and watch his talk as well if you like this topic. If we compare dynamic versus static approaches, we see where the advantages of the dynamic approaches lie. If we have a sophisticated static tool, then this static tool tries to determine runtime conditions before we actually do the compilation or the execution. So a sophisticated static program tries to estimate how the control flow of the program might be and does some loop heuristics, how often does this loop execute, and also do some data flow estimations, where starts my data in the program and where does it end. Dynamic tools doesn't need to do stuff like that. They know what the program is doing because they are the program, and they know where the data is flowing because they are processing the data. We have two classes here. We have the detection class and the prevention class. The detection class is somewhere in the middle between the static and the dynamic analysis. We've got one example here. It's called Stobo. This is for systematic testing of buffer overflows. And the name gives it already away. Stobo doesn't produce any production code. Stobo puts out an executable that is should be used solely for testing the program. The developer of Stobo say that they are a dynamic extension of Boone's approach, so we might have some familiarities there. Stobo does track the possible buffer lengths during execution, and actually I think I've done the wrong word in italics, because what Stobo does and what other dynamic approaches don't do is Stobo looks at the possible buffer lengths, not at the actual buffer lengths. We're going to see what this is or what is meant by that. The tool is supposed to accompany program testing, I already told you. So how does it work? The source code of our program gets altered before we compile it. So for every statement in our program that works on our buffers, we alter the source code. So all functions that could lead to buffer overflows, like string copy, get wrapper functions that only do the string copy but also do some checks. And if one of the wrapped functions detect a potential buffer overflow, we get a warning. Example here, we got our source code. So the declaration of a character buffer of the size 100 looks after Stobo worked on the source code like that. We still declare the buffer, but then we call a function called Stobo stack buff, where in the global table of so Stobo has a global table of all the buffers and all the buffer sizes, and this function just does memorize that buffer and the size of buff is available right now. If we do heap allocation, it looks like that. We also, Stobo also just declares a pointer, but the malloc is wrapped. So we don't call malloc directly, but we call Stobo const mem malloc. Stobo allocates the memory, but also does an entry in the global table that we have now a buffer called pointer with the size of 20. So if we do a string copy from buffer to pointer, Stobo uses its own, translates this to its own function, Stobo string copy. And Stobo string copy, before Stobo is executing the string copy, Stobo looks at the size of buffer. Stobo knows the buffer has the size 100, and Stobo looks at the size of pointer, and Stobo he sees, oh, we only have allocated 20 bytes for pointer. So we might have a problem here that in some time, even not with the actual data I'm working right now during the execution, but if somebody that is using the program is trying to overflow me, he might write too much memory or too much data in buffer and overflow pointer. So Stobo is able to notice that we might have here possible buffer overflow. again, Stobo looks at the potential sizes. Stobo doesn't know or doesn't care if right now, during the execution, buff may only contain the word foo. But it knows there might be a situation later in the program execution, or if somebody else tries to execute a program, where buffer actually contains all 100 bytes. And therefore, Stobo finds buffer overflows, that stuff like stack guard, not found by every time. And this is a good introduction to our next class, those dynamic tools that prevent the exploitation of buffer overflows. And they are the class of stack protectors, and at least this is the class I'm going to show you. There are some other approaches you should. I'm going to put a director's cut of my slides with all the missing tools up on the Congress website, and also with more information if you want to read a little about this. Stack protectors try to prevent the exploitation of buffer overflows by altering the underlying program semantics. So they some of them enhance the function prologue and epilogue. Some others might have something like a separate stack for the return addresses, and some others do reordering of local variables. The most common way for stack protectors are the ones that use canaries. Canaries or a canary value is something that is written on the stack that is supposed to protect our return address. So the dynamic tool is altering the compilation process. We've seen in the presentation right before me how the function prologue and epilogue looks like. The prologue does some stuff on the stack, and the epilogue does some pops. Those stack protectors add some code to the function prologue and epilogue to check if the canary is still valid. Just look at an example, then this should be easy to understand. We have a stack frame here with the function parameters, the return address, and then we have a canary value right in front of the return address. And then we have the saved frame pointer and our vulnerable buffer. If somebody tries to copy a shellcode into our buffer and do a buffer overflow, the shellcode is written to the buffer, written over the buffer boundaries, and is overwriting the canary value. When we return from this function, the function epilogue looks if the canary is still valid. If the canary is not the value we expect it to be, in this case it's LLCO, then an alert is produced and usually the program terminates. Yeah, canary gets overwritten, the attack and detected. There are a couple of different types of canaries that you can write on the stack. There's a random canary. This is just a random value, so that that attacker can't guess what canary might be used and use this in the shellcode at the right place. There's something like a random XOR canary. I don't think it's used in the wild anymore. Something like that we have a random canary that is XORed with our return address, so we have a different canary for every function. There's a null canary, and more interesting, the terminator canary, which is the special case of the null canary. The terminator canary contains all characters that cause unsafe library functions to stop writing to the buffers. So there's the null byte, the first thing, stops a string copy with this operation. I think the next one, the new line, is supposed to stop gets and fgets and so on. So the terminator canary is obviously that you can't construct a shellcode that contains the canary, or if you try to contain the canary into your shellcode, the overflow operation will be stopped. Yes, stack canaries only protect against buffer overflows that are trying to overwrite the return address. We have no protection against heap overflows for mastering exploits. Also, no real protection against pointer overwriting or the alteration of local variables. There are a couple of tools that use stack canaries. The most common or the most best known is stack guard. Then Microsoft tried to copy stack guard with their Visual Studio.NET compiler, but they did it really poorly and introduced new security vulnerabilities with the implementation. And GCC, I think, it now contains per default something it's called Propolis. It's development by IBM Research. And I'm going to show you how this works. It's, okay, additional programs, when canary, this is pretty obvious. If a canary violation gets detected, our program execution stops, and therefore we just alter our vulnerability from a remote code injection to denial of service, and I don't really want that on my web server as well. Okay, Propolis. Propolis does pretty much the same as other stack protectors. They use canaries as well, but they are a little bit, Propolis is a little bit smarter than the dumb stack protector I was showing you. Propolis reorders the values on the stack. So the local buffers are located, when you have a stack frame, are located between the local variables and the guard value. So if we have a local buffer and we have a buffer overflow, local variables don't get overridden anymore. So if we have a function pointer in our program and we have a buffer overflow, the buffer overflow is not able to override the function pointer anymore. Also, our saved frame pointer is protected by the guard value. There used to be exploits for simple stack guards where they just altered the frame pointer and not the return address and constructed a fake stack frame which contained then a fake return address. This attack is also prevented by Propolis. The only thing, if we look at this as stack frame layout, the only thing that is still overwritable, which could cause problems, are the function arguments. If we have function pointers in our function arguments that are dereferenced before the function returns, we may still be exploitable, but Propolis knows about that. So Propolis does protection of function arguments through local copies. If we have a function bar that expects a function pointer func as a parameter, without any protection, this function pointer can be overwritten by a buffer overflow of buff, and so func can point to anything we want func to point to. Propolis does this with our program. Propolis introduces a new local variable called local func, and the first thing it does is copying every function pointer argument of our program into this local copy. So the character buffer lies above this local func. So if we have a buffer overflow that is overflowing buff, the pointer, so the function parameter func is still overridden, but at a point of time where it doesn't has any significance anymore, because in the rest of the program, local func is used instead. So this attack doesn't work anymore. Propolis is not perfect. The Propolis is not able to reorder elements of or stuff that is hidden in structs. So if you have a struct that contains, for example, a buffer and a function pointer or stuff like that, then you're still out of luck and still exploitable. As well, it doesn't really protect the overwriting of pointer arrays. So if you have an array of function pointers, then we still are able to write into this buffer. Okay, conclusion, perfect timing. The conclusion is, I don't really know where we stand. I don't know what the current limitations of static analysis for security problems are. There are no good surveys to show us which kind of vulnerabilities are really detectable right now and which kind of vulnerabilities are not covered. This is something I do in my research. I want to find out what is possible today. Also, I'm not really sure what the actual ratio is between real vulnerabilities and false positives, because the more false positives we have, the more time it takes to work with the analysis results of our tools, and the more unwilling program managers or product managers are willing to use these tools, because if our development process takes 3 times longer because of those tools, we won't use them, I think. The static tools pretty much ignore completely C++. I think maybe it's too hard, I don't know, or if they think who's smart enough to use C++ is smart enough to write secure code. It's just an observation I made. Also, all the static tools I presented you have a narrow focus. They only do bounds checking, or they only look for mart strings or time of check, time of use. So if we want to find all our problems in our source code using these free tools, we have to use more than one tools on our code. So we have even more false positives, which kind of sucks. The commercial tools do everything in once. So they they are better in this direction. The dynamic tools have the problem they only attacked against known attack vectors.